This video has been supported by Keysight Technologies. Hey folks, I couldn't believe it either. After years of unsuccessful hunting for a 3458A multimeter, it looks like I'm getting two at the same time now. This one comes straight from Keysight, and OMG, isn't it magnificent? I think the number one reason for Keysight's redesign of the world's most linear multimeter was to ensure RoHS compliance. But while they were at it, they also gave it this beautiful new matte black everything design on top of the familiar user interface. I really like it. It's contrasty, immune to dirt and plastic discoloration. And if I'm ever getting robbed, nobody is going to take it because it looks like a VCR. This black box is 100% compatible to its popular predecessors. On one hand, that's great because setups won't have to be changed and operators won't have to be trained when updating a unit. On the other hand, that means that there's still only a GPIB interface to talk to, no USB or Ethernet, just like it was 30 years ago. One big improvement over my HP meter though, is how wonderfully quiet this thing is. I think I have equipped exactly the same Papst cooling fan in mine, but still this one manages to be a lot more subtle. Of course we'll take it apart in a moment, but before we dive deep into all the delicious, scandalous details, we've got a more pressing matter to attend to first. This meter arrived on July 15th, exactly 1 month after it had been factory calibrated by Keysight Malaysia. That makes it by far the freshest and the most trustworthy transfer standard that I ever had on my desk. So before doing anything else, I'm going to use it to calibrate all my other stuff with some form of traceability for the first time ever. With the simple one-dimensional standards like 10 volt, 10 kilo ohm and 1 ohm, that really just means to take some measurements and to write them down somewhere. I've done that occasionally over the past few months to make sure that none of the participants drift excessively. Especially this 1 ohm standard, which I bought untested off of a private eBay seller, had me worried. It is so easy and inviting to abuse it as a high current shunt. But no, to my great relief, everybody has been rock solid since July. No past abuse detectable. So now I know the values of my standards with the guaranteed accuracy that a new Keysight 3458A is delivered with. 1 ohm is sitting between 11 and 16 ppm above its nominal value. 10 kilo ohm is between 8 and 10 ppm higher, both depending a bit on their temperature. And my LTZ Mu 10 volt standard has last been seen at 126.5 ppm. Now don't get me wrong, I have complete confidence in Keysight Malaysia's calibration capabilities. Sure, I would have preferred if it said Loveland, Colorado on my certificate, purely for historic reasons. But I just so happen to live nearby one of the most distinguished metrology institutes in the world. And after some skillful pestering, they granted me an audience with even fresher ppms. Only one step removed from their primary quantum standards. That way I got another set of measurements at world-class accuracy for my spreadsheet. And the results are absolutely delightful. Let me show you why. You see, the 3458A's accuracies are specified in intervals. The newer its calibration, the more accurate it is specified to be, of course. Mine was older than 90 days at that time, so it has to be at least as accurate as the 1 year specification. In the 10 kilo ohm range, it showed me readings that were between 2 and 5 ppm lower than the actual value that we determined at the National Metrology Institute. Similar situation in the 10 ohm range, where I got readings that were between 3 and 8 ppm off. And finally, in the 10 volt range, readings were only missing half a ppm. Hope I didn't scare you away with a few numbers, because this is big. All the ranges I tested are either close to or downright within the tight 24-hour spec. And that is great news for all parties involved. We have not only shown that Keysight's factory calibration is perfect, but also that the range uncertainties are given quite conservatively, probably with harsher environments in mind. These guys can operate between 0 and 55 Celsius with full accuracy apparently. More about that in a minute. 2 more time-sensitive things to do first. 1. I'll hand over the fresh ppms to the lower floor while they are still warm. To the realm of questionable cable management where the Fluke calibrator is currently residing. This is the moment we've been waiting for since I gave it the once over last year. I have been saving its calibration self-check reports and uploading them to GitHub. I'm going to link those down below in case anybody is interested in the stability of this thing. But only now that I'm able to introduce some externally calibrated standards into the game does the data become meaningful and interesting. The other urgent matter is an AC adjustment for the HP unit. Normally you are supposed to use thermal RMS converters and read them with the meter's own freshly called DCV ranges to prepare very accurate signals for the AC calibration. I don't have those, but another whole meter with freshly calibrated AC ranges is going to do just as well. And that's pretty much it with the time-critical stuff that was breathing down my neck. Now the fresh ppms are cut and dry and we can proceed with the video in order. Where were we? Oh right, the Keysight 3458A was delivered with a few accessories. A power cord, the Cal certificate, and a pair of test leads. Those are nice silicone test leads with a few tip attachments, but they are hilariously unsuitable for metrology. Of course, no video would be complete without me mentioning my daily fix of pure copper spade connectors. Much better suited for ppm counting. They do, however, tarnish easily when touched with bare hands. The multimeter input jacks, on the other hand, are gold-plated tellurium copper, with similar low thermal EMF performance, but great immunity to oxidation. In my previous video about the grey HP meter, I focused mostly on the ingenious analog technology behind the scenes. Today I'd like to take a closer look at more practical details and applications instead, because the technical foundations are all the same in both meters. Let's start in the power on state where everybody lands after resetting or power cycling. Please don't power cycle these, it's impolite. The power on state has general purpose settings, not the most insanely accurate ones. Oh no, it's missing a whole digit, only 7.5 are displayed. To fix that, you press the blue shift key and then offset compensation, which has a blue N above it. That sends you to the menu, right to the N word. With N dig 9 you're getting your money's worth. Now all glorious 8.5 digits are displayed. But the least significant ones are a bit jumpy, don't you think? Like, is it 5 or 15? Make up your mind, please. Luckily, we can give the ADC more time to produce cleaner results. By pressing NPLC, you can specify how many power line cycles the ADC has to come to a conclusion. For example, 50 already makes a visible difference on the least significant digits. 100 is what's called for to reach most of the impressive spec sheet specs. Much longer integration times can be specified, but they yield diminishing returns in terms of noise rejection. But do you really have to configure all of this stuff by hand whenever resetting the meter? No, you can store 127 of your favorite configuration states in battery-backed memory slots and recall them at any time with 3 button presses. I quickly compared the DC volt noise performances of both meters at various integration times with copper short circuits installed. Because noise has become a matter of great interest to me recently. More about that soon, trademark. When looking at squiggly lines, the diminishing returns of longer integration times that I've just mentioned become more apparent. I would say the 100 NPLC setting that is also the basis for most of Keysight's datasheet specifications is a good go-to value for most applications. There was a fair bit of math involved in turning the raw samples into RMS voltages for a fair comparison. I'm going to link all of this stuff below if you want to have a closer look. Bottom line, both meters are practically equal, with the HP being a teeny tiny little bit better on paper. Next, one of my favorite features of these futuristic microprocessor-based voltmeters, their built-in math and statistics functions. No longer do you have to feed expensive pens and paper to an XY plotter. Oh, you don't even need a separate HPIB terminal for this. You just specify how many readings you want statistics of, start the math statistics program, and fill the readings buffer with measurements. Then, no matter if your readings are completed or not, you can check out the results of your math operations. In terms of statistics, there are things like min, max, average, percent, offset, and of course standard deviation, a single value that can tell you how good or bad a voltage reference is, for example. There are many more useful math functions, for example to convert the resistance thermometer readings into temperatures. Oh, look at all those microdegrees. In terms of AC voltages, the 3458A is a fantastic performer too. I've talked about the RMS converter hardware and the 3 available methods before. Analog computing for the fastest measurement speeds, random sampling for noise measurements, and synchronous subsampling for the most accurate measurements of repeating signals. I don't have a lot of AC experience myself, but word on the street is that thermal RMS converters are the way to go, when the ultimate AC accuracy is needed. Generally speaking, the 3458A tends to be as good or better than these for frequencies up to around 100 kHz, while conveniently having a much higher input impedance, a much wider input voltage range, and being much more robust. In the resistance ranges there are 2 settings one should know about to achieve enlightenment and the highest accuracy. First, a function called offset compensation measures the voltage over a resistor, while the resistance measurement current source is still disabled. That first measurement catches, for example, thermal EMFs from the test leads, so that they can be subtracted from the regular resistance measurements afterwards. This makes resistance measurements take a little bit longer, but the higher accuracy is usually worth it. The other setting is a simple time delay between a trigger event and the start of a measurement. No more than an extra second is needed for dielectric absorption effects in the meter and in the test leads to be saturated. Otherwise, those can corrupt the first few readings after changing ranges or connecting a new device under test. That, in combination with 4-wire mode, is the ultimate resistance measurement that this meter has to offer. A bench-bending collaboration of boat anchors would be necessary to get better readings on low resistances. Here I'm using the calibrator as a 100 mA current source to excite the 1 ohm standard, which brings our sense voltage a bit further away from noise and from thermal EMFs. We've got current capabilities too, but for once I don't have anything to say about them. It's cool that we can detect nanoampere directly. The fuse holder is hidden very well. You've got to kinda push in and twist out the bottom right binding post to eject an ordinary miniature glass fuse. No fancy sand-filled Bussmann as one would expect in fancy handheld multimeters, and that's okay because nobody would carry a 3458A to a murderous high-energy grid job. I hope. There is an interesting ratio mode that lets you measure 2 voltages between the normal input terminals and between the 4-wire sense terminals to determine, well, their ratio, so 1 if they are equal. This allows you to compare stuff like unknown input signals to an external standard, while avoiding most of the uncertainty contribution from the voltmeter itself or from a scanner card. Internally, this is done by 4 separate ADC conversions, 1 per terminal, and some number crunching. Of course, it's also very useful to compare resistances, if they are in a bridge configuration or if you have 2 very well matched current sources at hand. Here I'm using the HP meter as a current source. I'm calling this the interratio configuration. But yeah, that's pretty much the basics. The menu is still full of mysteries and possibilities, of which we have scratched only the surface. And so far we were only using the short version. Over here we can toggle the full menu and unlock even more obscure options I have no clue about. I'm sure we'll get to know more of them as time goes by and we start doing some actual projects with the meters. Oh, in case you were wondering what the HP unit is up to without displaying anything, it's just powered on permanently as good practice dictates. You can actually send 17 space characters using the display message command, as a kind of screensaver to prevent burn-in of the vacuum fluorescent display. But even without such excellent care, they last for decades. Speaking of long-term, I've sent the whole gang to a room of their own for a kind of group bonding activity. I want to compare everybody to everybody else, so that, for example, if one voltmeter claims that LTZ mu over here has lost a ppm, I can always get a second opinion from the other meter. And if both agree but claim that Fluke 732A with its 30 years of certified stability lost a similar ppm at a similar time, I would have reason to believe that we've got a more systematic problem on our hands. Now I can't just connect everybody to one common bus. The 10-volt standards would average each other out, and multiple meters with periodic auto-zero features would interfere with each other. So what I need are true one-on-one connections. I guess I could get a disposable, unpaid intern to make and break these connections for a few days straight. but I'd be afraid that their body heat would interfere with these sensitive measurements. So I'm going to use this low thermal EMF Ethernet switch, which is actually a relay scanner card that a fellow Voltnut has designed. It uses latching relays and a few other tricks to maintain the integrity of low voltage DC signals. It normally reaches a double-digit nanovolt offset within a few seconds after a switching operation. And that is just below the 3458A's least significant digit in the 10 volt range, so it's adequate for this task. I will link the GitHub repository for this useful PPM router below, and I'll connect mine to every participant and to a Raspberry Pi for control. This experiment took place at the height of summer, where the day-to-day ambient temperature changes in my rooftop apartment were at their absolute worst. I've recorded temperatures between 21 and 27 Celsius over the course of 1 month. For reference, a proper Cal lab is expected to be climatized at 23 plus minus half a degree on bad days maybe. So it's not surprising that my measurement results suffered a bit. It is a pleasant surprise, however, that my old HP unit, the light green trace, turned out to be almost completely immune to changes in ambient temperature. Whereas the new Keysight model with the red trace is matching its datasheet specification of half a ppm per degree Celsius precisely. Look what happens if I plot my room temperature in the same field as the Keysight measurement results. Wow, amazingly proportional these two values. I'd be tempted to try and improve the multimeter temperature coefficient in software based on this, if it didn't have something much better built in already. I'm talking about ACAL, one of the most distinguishing features in comparison to other long-scale multimeters. This function allows the 3458A to self-calibrate and to simply shrug off the effects of ambient temperature and the ravages of time. It seems a bit counterintuitive, doesn't it, that a meter suffers from temperature coefficient and aging, while having the technical ability to get rid of it all on its own? Well, it's actually pretty simple. It's based on our old friend the LTZ1000A ovenized voltage reference. Hidden inside of its own temperature-stabilized can, it couldn't care less about outside world weather. It drifts so little that it's the next best thing to negligible. The effects that we have just witnessed are coming mostly from the front end, from the input buffering and scaling, and from the ADC. All large components that are not so easy to ovenize. Instead, during an external cal against a known voltage standard, the meter also measures its own VREF through its own ADC and front end, and memorizes the value. Then, at any point in space and time and temperature, it can do that again, to find out almost exactly how far its own components have drifted since the last external cal. It uses a similar principle for resistances, and afterwards it's trivial to correct the measurement results mathematically if necessary, to compensate for the drift of nearly all internal components. Keysight's datasheet says it plainly: for the ultimate performance you have to run an auto-calibration like this, whenever the ambient temperature changes by 1 degree Celsius, or if it doesn't, once every 24 hours. I have now automated this in my data logging software. ACAL for the DC voltage ranges takes only about 3 minutes, so it's not too disruptive, and can just be run in the middle of a longer experiment. And here are the wonderful results of that change. We are now staying within half a ppm, or in other words, we are maintaining the 24-hour specification for over 10 days. So about as good as the classic HP meter had performed before. This data is also from winter, where my ambient temperatures tend to be controlled a bit better, thanks to radiators and thermostats. We can even ask for the calibration constants that are generated in the auto-calibration directly. A cal $72 command via GPIB will give us the DC voltage gain of the 10 volt range, and a temp command will return a momentary internal temperature reading. Logging just these two parameters over temperature and time while triggering frequent ACALs gives you a very good idea about the health and happiness of a 3458A, no external 10 volt standard necessary. A low Cal 72 peak-to-peak value indicates a low Tempco. And if the two lines are nice and proportional and not too independent from one another, it means that there's little long-term drift in the instrument, so you won't have to worry about an upcoming ADC defect. Since we are still all gathered here and the room temperatures are seasonably stable, I wanted to test one more thing. Linearity might be the most desirable voltmeter property overall. And it just so happens to be the one where 3458A is regarded as the world's best. Unfortunately, that's why I can't verify it. These multimeters are so exquisitely linear that what we measured here is actually the performance of my calibrator. A very linear voltage source on any other day. To verify my 3458As, I would need a few $100,000 programmable Josephson voltage source to generate a range of test voltages and see how far away my 3458A measurements are. Here I did it with a fluke calibrator anyway. The right axis and the blue line are the test sweep from -10 to +10 volt. The green and the red line are the deviations from the test voltage measured by HP and Keysight respectively, expressed in ppm of range. I think this is a perfectly understandable and intuitive representation. But equipment manufacturers and ADC datasheet writers often specify something called INL. Be it for customer deception or intercomparability, integral nonlinearity is the de facto standard. It takes a bit more math to remove gain and offset errors from my measurements. I'll link the Jupyter notebook below so you can check it out yourselves. If that is you want a good headache from my uncommented Python. Either way, with this kind of visualization one can tell that the HP and the Keysight meters are pretty much equivalent in terms of linearity. There is maybe a tenth of a ppm difference at negative full scale, but without quantum standards I couldn't tell which one is better. Similar story in the current ranges. The specifications of the calibrator are not quite as good as those of the Keysight multimeter, so I'm not quite sure whose performance is being tested here. However, the calibrator's current source is inside of a precisely temperature-controlled chamber, so we should be getting a lower Tempco at least. Sure enough, if we assume the current source Tempco to be 0, we'd get a very good 2 ppm per Celsius out of Keysight in the 1 mA range. It makes a bit of a strange jump as a response to sudden ambient temperature changes, but overall it's better than Hewlett-Packard, who's coming in with 4 to 5 ppm of range per Celsius worst case. Both much better than the datasheet figure, so no worries either way. Alright, now before we finally take a look under the hood, I wanted to point out one thing again. The new Keysight unit seems to have a much better thermal situation, at least on the front panel. Its display area is about 2 degrees Celsius cooler, but that doesn't matter much. The front input connectors, however, are also cooler and they don't have as much of a thermal gradient across them. That might actually be a measurable advantage for the Keysight. Let's see what other differences we can spot. Maybe something to explain the infinitesimal performance differences we've noticed. I'm not usually one to flaunt the latest trends in ESD fashion, but for this special occasion I strapped in without a moment's hesitation. Oh, there certainly are differences. I can already see why this one is developing a lot less heat. Wow, maybe I ought to rephrase my question and ask for things that haven't changed, rather than spotting differences because, well, almost everything is different. First of all, we've got a brand new OutGuard logic board that replaces 20 or so power-hungry integrated circuits with one Arctic 7 FPGA and a few requisites. First, I thought they had also implemented the 68,000 main processor in there as a soft-core maybe. The Xilinx would be able to do that with ease, I think. But on closer inspection there is a regular hardcore 68,000 in a QFP package sitting right next to it. Thank God they've also gotten rid of Dallas time bombs. The valuable calibration and configuration data is now memorized with the help of a normal coin cell, which is going to be much easier to source and replace. Each of these RAM chips is 1 megabit, so I guess the hardware option 1, extended reading memory that used to cost extra, is now included by default. The A1 board is almost entirely made in surface mount technology now. However, none of the working principles have changed as far as I can tell. Even the component placements and the reference designators have been inherited from the classic HP design. This way the public schematics remain mostly valid, and I suspect you can continue to mix and match modules of various generations of the meter to your heart's content. I don't think I've seen white Koto read relays before. They must have harvested these before they were fully ripe. The 2 bottom relays used to be Koto as well. Those are responsible for DC volt, so it makes perfect sense that those are special low thermal EMF types now. The voltage reference board, home to the mythical LTZ1000, is entirely unchanged. On these holy grounds they haven't even dared to switch to SMD construction. In my other meter I made a small modification here to lower the LTZ temperature, which should give me slightly lower long-term drift at the expense of no longer being able to operate the meter at 55 Celsius. Pretty sure I can live without that feature, but here I think I'm going to leave the stock configuration for now, so that we can judge how the meter drifts in its first few years of existence under normal circumstances. Right next to the VREF we've got a large Alpha Electronics 306F custom resistor network, which is responsible for scaling the LTZ output voltage to plus and minus 10 volt. Previously this network was in an inconspicuous DIP8 package, made by BI Technologies. I found no useful data about that part whatsoever. Now it seems to be made with Vishay's bulk metal foil technology, so it should be far superior now by the looks of it, but until I find out who's to blame for the worse Tempco that we've seen in the long-term test earlier, I'm going to keep this change in mind. Over here we still have the very influential DC input buffer or amplifier. Previously, HP claimed that they themselves were the manufacturer of the epoxy-dipped resistor network that sets the amplifier gains here. Nowadays the part has a different color and it's made by Vishay, but in the 10 volt range the amplifier is configured for unity gain without involvement of that network, so I don't think we are interested in this one. The shunt resistors for the current ranges, which I may have called not too impressive looking previously, are now positively awe-inspiring. They used to be small axial metal filmers or wire wounds. Now we've got some proper plastic molded Powertron foil, and you may have guessed it, that company belongs to Vishay Precision Group nowadays. The only hermetically sealed resistor is a 40K VHP 101. It's hanging out with the foil family over here, but it's got a more important job than the other current shunts. Its fantastically low Tempco makes it a great resistance standard for all the transfer functions involved in the self-calibration of the resistance and the current ranges. The constant current sources for resistance measurements are still based on a beautiful hermetic resistor network. This imposing hybrid is essentially nothing more than a high-voltage, high-power diode that sacrifices itself and tries to absorb as much energy as possible if somebody accidentally connects a high voltage to a resistance measurement. No exceptions. All of the leaded transistors in here, mostly single or dual matched JFETs, have a part number starting with LS. The Linear Systems website has datasheets, SPICE models, and spare part availability for most of them. That's wonderful. Before it was always a guessing game with HP internal part numbers. I haven't looked too deeply into all the SMD components, for example, but the changes that I have spotted on this board all seem very reasonable to me. The Pabst cooling fan is a 622L, a little bit less noisy and less powerful than the original in HP meters. It works great for this unit because it has fewer and more modern ICs that dissipate less power. Oh no, is all this dust coming from just half a year of operation at my place? That's unacceptable. Time for a class 1 clean room, or at least I'm going to get rid of my carpet. Time to visit the bottom side. This interface board that controls and reads the front panel, for example, has gotten no changes whatsoever. Not one SMD part has found its way on here, not even on the DC to DC converter module. The A2 board that converts AC into DC signals with proportional RMS values speaks yet another design language. Yellow silkscreen, some traces with square corners and no teardrops. There are some SMD components in the top right corner where previously an Elantec comparator lived. Obsolescence of the EL 2018 has given us quite a bit of trouble, and apparently Keysight too. Everything else is pretty much the same. Lots of analog switches, and our old friend the Teflon cable sample and hold capacitor is also still around. And for the finale we've got the legendary, the most linear commercially available analog to digital converter. It's still the same multi-slope ADC algorithm based on the U180 steering hybrid, but the surrounding and supporting circuitry is all new. 2 revisions before this board, the FPGA footprint was still a through-hole pin gate array, but FPGAs with 5V IOs were already on their way out. So they used to squeeze this guy with its entire entourage of level shifters onto a special daughter board, which would then fit into the pin gate array footprint. Now everybody is back on the same substrate, which is a cleaner solution. The last revision before this one was already in the SMD ROHS spirit. The keen eyes of the 3458A fan base have spotted an interesting logo on that one that didn't belong to Keysight. That gave rise to a lot of wild speculation, which you can still find on the EEV blog forum. I've asked around but received no official comments from anybody. So rather than recycling speculations, I'm just going to move on with what I know for sure. The third-party logo is gone from my board. Instead, we've got silkscreen for an unpopulated external sync hardware option. Above are test points for the steering hybrid's in-house voltage rails. The obsolescence of the Elantec comparators was particularly detrimental to this board, because it used multiple of them and relied particularly on their wide input voltage range. In that respect, there are absolutely no compatible replacement parts available from any manufacturer, no matter how hard you call their technical support centers. So whoever designed this circuit had to adapt and work with a different part. They came up with a pretty complicated constant current clamping circuit that limits the slope voltage without overloading or causing instabilities for the slope amplifier, all the while having minimal influence on the zero crossings. That seems to satisfy the Precision Texas Instruments comparator that they are using. None of this strikes me as an obvious contributor to temperature coefficient, but then again we are looking for only half a ppm per Celsius. Anything could cause such a small effect. Who knows, maybe even the addition of some decorative blinking lights, whose state corresponds to ADC cycles. Here's one conversion per NPLC, for example. And that concludes our teardown of the latest Keysight 3458A digital multimeter. I didn't look too deeply into all of the little details, but I think we've seen the most important ones. In an EEV blog interview with Keysight's John Kenny, I think I heard a hint about human resource issues. A shortage of greybeards from the Hewlett-Packard era may have given them some problems with this very redesign of the 3458A. That had me a little bit skeptical at first, but now I know that they've pulled it off alright. I wonder what will happen if we just swap the ADC boards. It's unnecessary and reckless, but once the idea had formed, I knew I couldn't go on before finding out. Hey, if anything goes wrong, at least the A3 board no longer costs as much. Keysight has recently lowered the price from 3 to around 1K. It's still a fair bit of money if you look at it as an ADC. But for the most linear one, and to save a legendary 3458A from the landfill, I would say it's a completely fair price now. Alright then, let's see if that works. Yeah, look, it does work. Fantastic. The latest LED-free SMD ADC is fully backward compatible with some of the oldest hardware, with firmware 9.2 being installed on both of them. The calibrations saved on the meter's digital boards don't work particularly well for different hardware, of course. And I haven't found out where the half ppm Tempco is coming from. In this quick test I got about half a ppm from the HP body with the Keysight ADC, but the Keysight body with the HP ADC was only marginally better. So I'm putting everything back where it belongs. And that's finally all. In conclusion, I would say that with the RoHS compliance done, there is nothing that could get in the way of a few more decades of success for the 3458A. Since the main processor board has been shrunken in half, the compartment it sits in is looking almost a little empty. That's room for innovation right there. Even just an Ethernet jack would be wonderful to have in the future. As of right now, it's a modernized, deeply backwards compatible design iteration, with lower power and generally higher quality components. The key features linearity, stability, accuracy or speed, self-calibration and a moderate price have been preserved. The unit I received has a slightly elevated temperature coefficient in the 10 volt DC range. But that's not a big deal because A, the meter can help itself, and B, I bet there are no serious 3458A users in the world that don't have climate control. A huge thanks to Keysight Technologies for sending over such a powerful tool that will help me make better electrometrology videos in the future. And thanks to all of you for watching. If your lab needs some black Keysight test and measurement equipment too, you should consider participating in this year's Keysight Live from the Lab event. Starting May 17th, there will be hands-on engineering tips and tricks, interviews with industry experts and your favorite electronic engineering YouTubers. And as if that wasn't good enough, over $100,000 in test gear giveaways. Sign up for free with a link in the description for one bonus entry into the drawing. I'm wishing you a ton of good luck.